Morning, good afternoon, and good night, Professor. My name is Pan Lizhen, and today I will be presenting my assessment fee for BA 514 AI and decision making. So in this project, I developed and evaluated machine learning models to predict retail transaction revenue and explore how the predictions could support practical business decision making. So this presentation is divided into 8 main sections. So I will first introduce the dataset through descriptive statistic and EDA. Then I will discuss the research questions, data preprocessing and leakage control, followed by feature engineering and model development. After that, I will compare the model performance, examine bias and fairness across product segments, discuss the business recommendations, and finally conclude with the limitations and potential future work. So let's begin with an overview of the dataset. So as shown in the table, the dataset contains 68,868 observations covering 24 weeks, 44 brands, and 111 subcategories. So the total revenue recorded in the dataset is around 8.5 million ringgit Malaysia. So looking at the descriptive statistic, the original selling price has a mean of 152 ringgit 23 cent, with values ranging from 15 ringgits to 569 ringgits. So the average revenue per observation is at 123 ringgit 40 cent, with a standard deviation of 70 ringgit 77 cent. So for units sold, the mean is only 1.03. So while the median for both the 25th and 75th percentiles are 1. So this indicates that majority of the observations involve only 1 unit sold. The average discount percentage is around 19.1%, range from 1% to almost 90%. Therefore, discounting is an important characteristic of the dataset, and it may potentially influence the prediction of the revenue. So overall, these description statistics show that the dataset contains meaningful variation in price, discount, and revenue, which provides a suitable basis for developing predictive models. So moving to the first EDA, this figure is actually showing the total revenue across 24-week periods, with major peaks around week 26 to 27, and another increase around weeks 39 to 41. So this suggests that revenue is influenced by temporal factors such as promotion or business activities. Therefore, I retain week as a predictive variable and use a chronological trend validation test split in the modeling part later to reflect a more realistic future prediction scenario. So the second EDA shows the top 10 brands ranked by total revenue. We can see that revenue is concentrated among a relatively small number of brands, with brand C3 being the strongest contributor, followed by brand C83 and brand C77. So this suggests that brand is an important predictive feature, and the high-performing brands may deserve greater attention in inventory and promotional planning. And the last EDA is a histogram showing the distribution of discount percentage. So most observations are concentrated around specific discount ranges, suggesting that discounts are applied based on structured promotional tiers rather than randomly. So this supports retaining discount percentage as a predictive variable. However, its importance in the model should be interpreted as a predictive relationship instead of the proof that higher discount directly cause higher revenue. Based on the dataset and EDA, I developed 1 main research questions and 3 secondary questions. So the main questions is whether product pricing, promotional and temporal factors can predict retail revenue, and which model is actually performing the best. And the secondary questions examine the key predictors, whether model performance differs across product segments, and how the results can support business decision. Together, these questions ensure that the project does not focus only on achieving a high accuracy score. Instead, it's also considered interpretability, fairness, and practical decision making. So before building the predictive models, I conducted a data audit. First of all, there's no missing values or duplicate rows were found in the dataset. And you can see there are 2 tables here. The first table on the left summarizes the variables that were excluded and retained. So the excluded variables including unit sold, discount in RM, discount per unit, identifiers, and constant variables. The most important reason for excluding this variable is to control leakage. And on the right, I retain variables such as price, discount percentage, product, brand, category, and week, because these provide information that could reasonably be available before the revenue outcome is observed. So the second table shows the chronological data split. So week 24 to 38 were used for training, week 39 to 41 for validation, and weeks 42 to 47 were reserved as the final test set. So the approach is more realistic because the model is trained on earlier periods and evaluated on future periods. So my next step was feature engineering and model development. To incorporate historical business information, I created leakage Ceph prior mean revenue features for product, brand, and subcategory. The key principle here is that for any observation, the historical average was calculated only using information from the previous period. Therefore, the model does not have access to future revenue information. So the table here is actually comparing the 2 machine learning approaches that apply in the study. So the first model is ridge regression, which serves as a regularized linear benchmark. It provides a relative simple model for comparison. And the second model is CatBoost, which is a non-linear machine learning algorithm, and it's particularly useful here because the dataset contains categorical variables with relatively high cardinality, such as product and brands. Hyperparameters were selected using the validation period only. The final test period was kept untouched until the final evaluation, which helps to provide a more unbiased comparison between the model. Next, this table here compares the performance of three approaches using MAE, RMSE, and R-square. So the first row is a mean baseline. This is a simple benchmark that predicts the average revenue. It has an RMSE of 71 ringgit 4 cent and a negative R-square, showing that it's actually performed poorly, right? The second model is ridge regression. So the performance improved significantly, achieving an MAE of 6 ringgit 69 cent, RMSE of 13 ringgit 66 cent, and a R-square of 0.957. However, the strongest performance comes from the CatBoost regressor. So CatBoost achieves the lower MAE of 4 ringgit 18 cent, the lowest RMSE of 9 ringgit 47 cent, and the highest R-square of 0.979. So therefore, CatBoost is selected as the final model. This result suggests that there are nonlinear relationships and interactions within the data that CatBoost is able to capture more effectively than the linear ridge regression model. So you can see here the scattered plot on the right compares the actual and predicted revenue. Most points are close to the diagonal line, indicating strong predictive accuracy and supporting the R-square of 0.979. However, some outliers remain, showing occasionally under or over predictions. The top left chart shows the features importance. Original selling price is the strongest predictors at 77.69%, followed by the discount percentage as 18.5%, indicating that pricing and promotional factors are the main drivers for the model's predictions. And finally, the error distribution show that most predictions errors are close to zero, so further confirming the model's overall accuracy. However, some larger errors remain, so the model should be used as a decision support tool only rather than rely on completely for individual prediction. So besides the overall accuracy, I also examine whether the model performs differently across product gender segment. The table here shows the sample size and prediction errors for each group. So the men's and women's segment have relatively low MAE value, while some smaller segment have higher prediction errors. Among group with at least hundreds of observations, the difference between highest and lowest MAE is around 1.95 times. So this does not necessarily indicate discrimination, as the differences may be influenced by factors such as sample size or different product characteristics. However, it shows that the overall model accuracy may not be constant across every segment. Therefore, if the model is implemented, its prediction performance should be monitored across different product segments. So based on the modeling and fairness result, I developed 4 practical recommendations. So the first one, revenue planning. The model can support revenue planning before any campaigns are launched, right? For example, management could use the model to estimate expected revenue for a particular brand or product group before committing marketing resource to a campaign or to an event. And second, promotion and discount events. So because price and discount percentage are the strongest predictive variables, the business can use the model to compare different promotional scenarios. For example, instead of immediately launching a 30% discount, right, management could compare the predicted revenue under 10, 20, or 30% discount scenario. This can help support a more data-driven promotional decision. And third, the brand and subcategory planning. So the EDA show the revenue is concentrated among certain brands. Therefore, high-performing brands for subcategories, right, could receive greater attention in inventory planning and campaign placement. On the other hand, the lower-performing products could be targeted with more specific promotional strategies rather than receiving the same level of resources. And last but not least, the fairness monitoring and governance. So model performance should be monitored continuously across product segment. If a particular segment constantly has higher prediction errors, the business should investigate whether the issue is related to limited data, different product characteristic, or insufficient historical information. Importantly, human approval should remain part of the decision-making process, particularly for significant pricing or promotion decision. So to conclude, this project developed a predictive model for retail transaction revenue using product pricing, promotional, and temporal information. Among the model tested, CatBoost was the strongest model, achieving an R-square of 0.979 on the future week test set. The two dominant predictive variables are original selling price and discount percentage. However, strong aggregate performance does not mean that model is equally reliable for every observation or product segment. So the actual versus predicted plot and the fairness analysis both shows that predictions errors still exist, right? So there are several limitations for the study. The data set only covers a 24-week period. The data is observational, and there are no verified customer level demographic variables. So for future work, the model could be improved using multi-year data, richer inventory and promotional features, as well as rolling origin validation. Overall, my key takeaways of this assignment is that predictive accuracy alone is not sufficient. The most reliable use of AI in this context is to combine predictive accuracy with error monitoring, fairness check, governance, and human judgment. Right. So that concludes my presentation. Thank you very much for your time and attention. See ya.